but he also just got an award. Where is that? Oh, down there. He got the Occultation Group at UVA. They won a nice award in 2025. He is currently also a member of the officers. He's the secretary. And whenever you're ready.
Great.
Recording?
It is recording. I've just checked. I've got one. Thank you. So most of you guys know me. I'm Teddy. I'm going to keep this very informal. I'm going to kind of look at my slides and remember what I wrote down. If you have questions, just raise your hand. There's not some lecture. It's kind of just a fun talk about asteroids. Asteroids, I think, are kind of fun from an amateur astronomer or a visual astronomer's point of view because they're not quite as impressive as the grand planets are. But if you're dedicated enough, you can, like Boris was talking about earlier, watch them and track them throughout the sky. And they're fascinating objects in my mind. But kind of taking a step back, this talk is about asteroids and asteroid occultations. I joke actually that it's the occult sciences. I'll be talking about occultations tonight, which are a way of studying asteroids. And I'll get onto exactly what they are, what occultations are in a minute. But to take a step back, we first should address what an asteroid actually is. We use this term minor planets, which sounds like it's a very specific designation for a set of bodies in the solar system. It's actually pretty much anything that isn't a planet. So regrettably, Pluto and on down to meter and sub-meter scale objects are all minor planets. Although I think Pluto is a planet in most of our hearts. It is what we would classify as a minor planet. And there's a lot of different types of these things. There's a lot of populations of them. We're most familiar with the main belt of asteroids in between the planets Mars and Jupiter, because it's the closest one to us that has the most influence on our day-to-day life, at least our day-to-day life, maybe not the general population's day-to-day life. And there's about 1.3 million of these things out there across the separate populations of asteroids, the main belt, the Kuiper belt, the Trojans, and all of the other little populations. So here are the populations I was talking about. We have this the classic asteroid belt between the orbits of Mars and Jupiter. It's a relatively stable population of asteroids. Jupiter's orbit actually tends to perturb or disturb a lot of the asteroids in here, which means they dynamically have been evolving for the past 4.5 billion years or so since the solar system formed. Which means that we consider this subset of asteroids not younger perhaps, but it's a dynamically changing set of asteroids. Compare this to the Trojan population of asteroids, which actually rests in a Lagrange point, which is basically a point in Jupiter's orbit where the forces of gravity from Jupiter and the sun equal out, and it's kind of a well. And these asteroids drifted in here a long time ago, and basically haven't moved since, because there's not a whole lot of force acting on them to move. This subset of asteroids is a much more ancient population, we think, and it's much more representative of what the early solar system looked like. And so I'll get more on this later, but there's a specific spacecraft mission that NASA has built to visit this subset of asteroids to learn about the processes that this early solar system formed in. And it's a really interesting mission because there's a lot of occultations. And then if you zoom all the way out here, these are the two populations I was just telling you about, the asteroid belt and the Trojan belt. And then there's this kind of petri dish scattering of other bodies in a sphere around the sun, which is the Kuiper belt and the Oort cloud. So we've got this nice planar distribution across the 2D plane of the solar system for these bodies, roughly planar. And then if you go out this far to the outer solar system, these are very eccentric bodies. They're orbiting at weird inclinations to the sun. Some of them have orbital periods of thousands of years. This is where a lot of the comet population comes from. So I call this an asteroid group, but when you're getting out to this far away from the sun, you're looking at a lot of comets, dwarf planets like Pluto, Haumea, Makemake, Eris, Quaoar, which I'll talk about later, excitingly. A lot of really cool bodies out there. There's a lot of really interesting stuff, and I'll talk about some fun ones that we studied recently. And I don't think I included a picture of what one of those is. It's okay. So who here kind of has an idea of what an asteroid looks like? We're all kind of familiar. They're different shapes and sizes, but they're mostly rocks in space. The interesting thing comes to what type of rocks they are and if they're clumps of loosely held together rubble. And there's a lot of interesting science you can do there, which is kind of what we deal in. But if you want to take a picture of these things, these are two pictures of the same minor planet called Arakoth in the outer solar system. The left one is taken with the Hubble Space Telescope. Oh, my formatting's gotten screwed up, but it's about $10 billion to build that telescope. Not exactly amateur astronomy budget. I don't think Cass is quite there yet on our. Although Daniel's trying, I don't think we're quite there. And it's a pixel or two, so it's you're spending $10 billion for, you can probably count them, 7 or 8 pixels worth of asteroid. The other option you've got, if you want to get a really good study on an asteroid, is a spacecraft. And spacecraft are wonderful. We love spacecraft, visiting these things. It's a really clear picture. It took about 13 years to travel from Earth. This is the New Horizons spacecraft. Travel from Earth to Arakoth. And cheaper, certainly, but still about 500 million, which we're closer to, but we're still, I would say, a few orders of magnitude away from purchasing our own Charlottesville Astronomical Society spacecraft. So both of these are kind of out of the budget of most research institutions, and while they provide really valuable data sets on the composition, the size, the shape, and the orbits of these asteroids, if you want to know more about these asteroids and you want to learn more about the conditions that formed these asteroids, you got to find a cheaper way. So keep in mind, this is a regular telescope on the left. If you use a smaller telescope, you're actually getting a worse picture than this. So most telescopes, if you're taking a direct picture of these asteroids, do not reveal a lot about the shape and size of asteroids. Luckily, there's another option. And these are my favorite things to study in astronomy. These are called stellar occultations. So when an asteroid or any other solar system body, but particularly here an asteroid, passes in front of a star, it casts a shadow across the surface of the Earth. Did anyone travel? I'm presuming many of us traveled to observe the solar eclipse last year, right? So and if you didn't, you've likely seen the maps that they have where you can see the path of totality across the United States and the path of penumbra or umbra and penumbra. It's a very similar premise to an asteroid occultation is a very similar premise to an eclipse. There's a few notable differences. The first is that you're occulting a star, which is practically infinitely far away as far as you can treat it for all intents and purposes as an infinitely far away point source, as opposed to the sun, which is definitely not a point source in the sky. And the asteroids are usually quite far away as well. And so there's usually not an umbra and a penumbra of these occultations. There are usually, it's usually a direct translation, if not slightly broader or narrower, depending on the event. So there's a geometric, you can assign a geometric ratio from the shadow cast on Earth to the asteroid being occulted. This is, for example, an occultation by the dwarf planet Quaoar in the far reaches of the solar system. And you can see as this is a much sped up version. It's a very big object. It's about 1,000 kilometers wide on average. But as it passes in front of the star, the light from the star completely disappears. And then it comes back. And you can actually, I'm going to skip ahead 2 slides. But you can measure the dip in brightness. This is a different asteroid, but it's the same principle. You can measure the dip in brightness that you see with your telescope, and plot that along with your geospatial distribution across the Earth if you have multiple telescopes, and reconstruct a frighteningly accurate profile of what these asteroids look like. So, for example, this station up here, 2, for example, did not see the star disappear. Station number 3, let's say, saw the star disappear for 1 second. Station 5 they're kind of hidden, but let's go down to station 14, probably saw it for 7 or 8 seconds. 20 saw it for 10 seconds, 12 seconds. And if you can reconstruct where the telescopes are spread out across this shadow path, you can then reconstruct almost precisely what the asteroid looks like. Does that make sense? Questions on any of that? That's kind of the most critical phenomena to understand with asteroid occultations and how you can reconstruct what the asteroid looks like. So if there are questions, this is the time to ask them.
Typically is the belt width there? I'm sure it's in miles.
So it's it actually depends. It's like I said. So I wish I had a yeah. So it's I was hoping to I was going to see if I could use that whiteboard, but I think I can get by without the whiteboard. So it's practically a direct sorry, I don't think I need it. A translation of the width of the asteroid. So it's entirely dependent on the width of the asteroid, and it's usually almost identical to the asteroid width because both sources are so far away from Earth. The shadows they cast are practically so an 8-kilometer wide asteroid is going to cast a shadow on the order of 8 kilometers wide, if not slightly smaller or larger. Yeah, it depends. Yeah, if not slightly larger. But it's very close to the width of the asteroid. There are some occultations by minor planets that are very large. For example, Quaoar, 1,000 kilometers. The shadows cast by Quaoar are about 1,000 kilometers wide, and so they take up a big swath of the Earth's surface. But these are very easy to predict. So we have great measurements on about 250,000 of the population of 1.3 million asteroids in the solar system. And so if we cross-reference the orbits of these asteroids with the well-known positions of almost every star in the night sky that goes down to 15th, 16th magnitude, we generate predictions for, you can very easily generate predictions for these asteroids.
I got a question about the blue line there.
Yes.
It doesn't even, no, not there.
Oh, excuse me.
There. Right.
Oh, this is a very old one. I'll show you some examples of more modern fits.
Not these means.
Exactly, yeah. So I picked this one a long time ago. I should really update the figure in this plot. More modern techniques to fit the shapes of these profiles allow for a more human shape fit. So you can kind of coax if you have relatively constrained error. I think the errors on these older data points are quite uncertain. As you can see, this is a light curve that was generated to fit. This shape is fit from light curves that looked like this. This was taken about 25 years ago. So the uncertainty on these noise measurements are quite large. And so this data point is centered here, but it could be anywhere between here and here. And same with all of these. So it's, that's where my guess is the shape came from this one. But as video techniques have improved significantly over the past 20 or 25 years with CCD and CMOS cameras, the sensitivity on these measurements has increased significantly. So the rotation periods for these things are the fastest rotating asteroids are about 2 hours or so, and the longest occultation that will pass Earth is on the order of, depending on the object and the relative motions of Earth, the longest you'll usually see is about 30 minutes. So in certain cases, if you have observers who are, let's say in Baja California or California Sur, and somebody in the DR, you actually do have to account for the rotation of the asteroid in that profile. And I have a really good example of what that looks like, but I can't show you it because it's under scientific embargo right now. I don't have permission from the project leader to share that picture, but I really like to because it's really cool. We had observers, I think somebody in Idaho and somebody, we were in New York for an occultation, and you actually do have to account for the rotation of the asteroid as it is passing in front of the star to align the chords, as we call them. Each of these lines I'll call a chord in the future, C-H-O-R-D. The point being that you can take a relatively small telescope and observe a relatively bright star as a very, very, very faint asteroid passes in front of it and blocks the light out from the star. And from that information, reconstruct a very, very precise measurement or shape of what this asteroid looks like.
How do you know it's actually rotating? What information do you get that says that
so that is one of the few things that is very easy to obtain from photometric analysis. So just pointing a telescope at it and observing the light of the asteroid as it changes. So you can point a regular or a large-ish telescope at an asteroid, take a picture, 30 minutes later take another picture, 30 minutes later take another picture, and you can see the brightness change as it's rotating and reflecting sunlight differently. And that's actually quite obvious from just regular photometry, as you'd call it, so taking pictures of these asteroids. And as the different parts of the asteroid reflect sunlight differently, there's nooks and crannies and boulders and different morphology on all sides of the asteroid. You can see the same patterns occur over periods, and that's one of the easiest ways to identify if an asteroid has a satellite or a moon or something, because you'll see multiple synchronous patterns within the larger wave function of the asteroid. So who are we? What does the UVA Occultation Group have to do with any of this? If you're, we have luckily one of our member observers in the audience right now, Georgia, if you want to wave. Georgia's been working with us for a long time, since she was at CHS. This is all we do. We do asteroid occultations and nothing else. We live to watch stars disappear. And I'll say it's a pretty magical thing. I'd love to do something with Cass at some point and share what an asteroid occultation actually looks like in real time, because it's really something special. You literally are looking at a star in real time on your laptop through a camera attached to your telescope, and it's there for however long, and then for a second or two, it's gone, and then it comes right back. And so it's fun, and it's also really, really valuable science, specifically for spacecraft teams and other purposes, which I'll explain in a minute. We visited 19 states across the United States to observe these occultations in 4 different countries. The fun thing about occultations is you don't get to pick when and where the asteroids pass in front of stars. They have to pass in front of, they choose when they pass in front of stars, and they choose what part of the Earth they cross over. So this is not one that we observed, but we did have a member observe from Baja California for a very important asteroid a few years ago.
Hey, Teddy, you had said once before that it's the Occultation Group at UVA.
Oh yeah, but this isn't for yeah.
So if UVA is not supporting, how do you get money to do the travel?
Oh, that's the fun part. I'll talk a little bit about that later if there's time. It's less interesting than you think, and it's something that is an ever-present issue with our group. We are constantly asking for money after we've done the thing that needs the money. Yeah, these are some fun pictures of us in the field. We do a lot of, we used to, they've kind of stopped working recently, but there is is anyone familiar with the Lucy spacecraft? The PI of it visited Cass a few years ago, Hal Levinson, that's him right there in the middle of us, the much younger me in the back row. So the Lucy spacecraft is visiting this population of Trojan asteroids I was telling you about earlier, which is this ancient, very, very ancient ring of asteroids sharing an orbit with Jupiter. They call it Lucy because Lucy is the primordial human ancestor discovered in the 60s in Ethiopia. And they view these asteroids as the primordial ancestors to all of the planets in the solar system, because these have been around for longer, undisturbed than most of the planets, who have evolved constantly through interactions with their neighbors and bombardments from you mentioned the Shoemaker-Levy 9 comet crash into Jupiter. Things like that happen all the time, but not very often in the Trojan belt. So they're visiting a prehistoric era in the solar system. So it's visiting 7 of these or 7 targets, 5 of which are Trojan asteroids. This is a list of all of the asteroid targets of this spacecraft. And one of the most important things the spacecraft team wants to know before it gets to these asteroids is they want to do a survey of them so that they know if they have any satellite moons, if there's anything interesting they should look out for and prime their instruments for. The instruments all require a 3 or 4 week lead time to send the commands to the spacecraft to make sure that there aren't any issues with executing those commands. And if they learn that there's a satellite moon 3 days before the flyby, they don't really have time to adjust the instruments to also take a picture or measure the properties of this asteroidal moon in the time. There's also a second reason why you want to know if there's a moon around these asteroids, which is that if you're spending the $500 million that you are to build one of these things, you really don't want to have it get into a crash once it reaches the first target it's going to. Interplanetary crashes, insurance doesn't cover those yet, I don't think. So they really want to avoid them to keep their premiums low. And in any case, of this survey, of this set of asteroids, These three were all of them have had coordinated occultation campaigns, but the UVA team has participated in these three bolded expeditions, some of which several times. This is a really cool one. It's a binary asteroid. Actually, so is Ptolemy, but they didn't know that before they did the campaign. But I'll get to that in a minute. There's another spacecraft that we're interested in. It's the MBR Explorer spacecraft. This one's a little bit more niche, I'd say, right now because it hasn't quite launched yet. The United Arab Emirates is building this spacecraft. It's set to launch in 2028. It's visiting 7 main belt asteroids. And of those 7, we have already, UVA has led, our team has led a series of campaigns to characterize for the first time this asteroid right here, 59980 1999 SG6. You're looking at this list and you might say to yourself, man, those first 4 have really catchy names, and I can remember if you read them off to me, I'd know what they were. I could probably read them back to you in 10 seconds. But those last 3 are what we call at least telephone numbers because they're kind of just a string of random numbers. The first is the identifier, and the second one is the date and the month it was discovered in. It's code for that, basically. All of what you can infer from the fact that these don't have names yet is that they're very poorly characterized. And so the UVA group has made it a priority of ours to lead some efforts to preliminarily qualify what these asteroids look like. The first 4 have some data on them. Justitia has had a wonderful campaign expedition to tell us what it looks like on a broad scale. Chimera 2 as well. Westerwald and Rockrex kind of, but these last 2 don't have names yet. So we don't know the first damn thing about them. And so UVA has taken it upon ourselves we've launched 3 campaigns to observe 59980 1999 SG6. And I'm talking about all of that in just a minute. But first, I want to cover what we do from here, because we do most of our work from Charlottesville. I call these stay-at-home occultations because they're, like Kevin likes to say, you get to go set up your telescope and then go inside, and he gets a glass of Merlot, but we usually have coffee. Yeah, so they're stay-at-home. So most of our work is done from the garage outside the Department of Astronomy at UVA. So you drive past us on the way up to the observatory. If you drive up at night and there's an open sky above you, you can bet a lot of money, I don't know how much you'd be willing to spend, that we'd be out there with the telescope. If it's clear, we've got a telescope out. We've got it right now. 15 minutes ago, there was an occultation. We have members down there right now observing it. And they're there all night, every time it's clear. Very dedicated group of observers. And we observe until 3, 4, 5, 6 a.m. In the morning every night. That's where we do most of the time. I am currently working on a project, which I'm working on a good name for it. Right now, it's the Virginia Coordinated Occultation Timing Array. Doesn't acronymize very well. VCOTA. I want something better than that, but I haven't found it quite yet. But what it will be in the end is an array of remotely operated observatories across Charlottesville. So right now, these 3 blue observatories are observatories which are already observing occultations every single night. If you're standing on one point on the surface of Earth, on any given night, about 40 asteroids are likely to occult a star with any likelihood above 1%. Maybe 3 or 4 of those are above 10 or 20%. The vast majority of asteroids in the solar system are not very well constrained on their orbits, and so they have great uncertainties in their position, which means that you could I wish I should have put a good picture of that in there. The shadow width could be hundreds of kilometers. The uncertainty could be hundreds of kilometers wide for a 5-kilometer wide asteroid.
Those are numbers for a occulting star, but that implicitly probably has in it a magnitude of the star. So what are you talking about in terms of?
We go down to, for our largest telescope, which is a 24-inch Dobsonian right here, we go down to 16th mag. Okay. The magnitude is important, but equally as important is the duration of the event. So a longer event can be observed for a fainter star because you can integrate your image for longer. But for these smaller 11-inch telescopes, we have optics on them that, well, we have additional optics that actually allow us to push down to 15th magnitude, which is pretty damn close to what the 24-inch can do. And we're observing events that are a quarter of a second long at 15th or 16th
So the
magnitude.
numbers you initially quoted, though, do you know what the magnitudes?
Oh, that's going down to 16th mag. Yeah.
Okay.
And at 15th mag, there are 40 events that you could do that also include below 1%. There's a lot of events that will happen, but most of it is a function of the uncertainty in the astrometry of the asteroid. So these smaller asteroids, the sub 10 kilometer, sub 5 kilometer, sub 2 kilometer, have enormous uncertainties on where they actually are. So the shadows they cast across Charlottesville are pretty much can often stretch or exceed the distance between these two observatories, Fan Mountain and one of our professors' houses. And so the idea is we'd like to construct an array of telescopes that basically spans this distance, so that if an asteroid if there's an uncertain occultation which is likely to pass over this region, at least one of those will get a hit. And once you get a hit on that asteroid, the uncertainty, that was loud, smacks down to 0. So basically, you've got, and I talk a little bit more about this later, but once you have one hit on on an asteroid with an occultation, you know exactly where that is, because you are looking at a sub-millisecond accuracy in your timing, and you're looking at a milli-arcsecond spatial resolution because of what the star is known to that precision from the Gaia satellite. Everyone, should I explain what Gaia is? People know what Gaia. It's a European Space Agency satellite which has mapped where all the stars in the galaxy are, and they know the accuracy of where these stars are into the milli-arcsecond or sub-milli-arcsecond level. So if you know that the asteroid was at that star at this sub-millisecond time, you have a really, really, really good idea of where it is.
Teddy, you could actually, if you're doing an occultation with a particular star, right?
Right.
And you know the direction that the asteroid is going, 20 minutes later, you could check an occultation on a different star, right? That same asteroid on a different star.
Well, I'll get to that in a second, actually. But so on a given night, so the angular sizes of these are actually quite small, and so even though a star might seem to be quite large on a video screen, the angle at sub-10s is actually quite small. So unless it's passing through a very, very crowded field of stars, an asteroid is passing through a very, very crowded field of stars, the likelihood of it occulting another star in the same night is, I've only seen it once or twice. And there's one that we were hoping to get maybe from the Emirates next summer, but it's quite rare because even though they're in the solar system, the angle of these asteroids that they subtend is quite small, and so are the stellar diameters.
So would you really be looking to make a ring of telescopes around Charlottesville?
Kind of.
They can come across.
Yeah, they can come at lots of different angles. So the distribution here is actually built largely on where the existing telescopes are. The majority of events pass by in the plane of the solar system. So roughly east-west with a 27-degree inclination based on the Earth's orientation. But you're right, they come at all kinds of different angles. And when you're looking at these trans-Neptunian objects, they can go up and down. They can go in all kinds of ways. And so this is a rough plan. The biggest actually issue is finding places to put the telescopes that will allow us to build a shed on their property. But we've looked for ones which basically we've prioritized the north-south distribution because that will provide the most even one for the majority of occultations. This was funded, I should say, by the Planetary Society, the Shoemaker NEO grant. So we've been funded specifically to search for these NEOs and provide continued observations on near-Earth object and specifically potentially hazardous asteroids to make sure that we know where these orbits are.
We've got a question online from Marshall Finkish. Can occultation technology be used to discover new asteroids?
It can, although it's difficult. That's part of one of the subtasks I'm hoping to work on for my thesis or one of the major tasks is to write an automatic photometry software which will measure and present you with a light curve for the asteroid that shows the dip. And once you have that, you can actually do it for pretty much every star in the field. And the hope is that once we have that, you might at some point discover that a random star in the background field of your event has been occulted by an object in the distant solar system. The problem is you don't have a great measurement of which direction the asteroid is going from there, because all you're seeing is the star go away. And so if you have a star here and it disappears for a second and then comes back, you don't know if it's because an asteroid is going that way, or it's going that way, or it's going that way, or it's going that way. And so you have to have pretty quick follow-up time with a very big telescope to see where the thing that occulted it actually is. But it's possible. So yeah, cool. I'm really excited to share this. I would like to give an enormous thank you to Leo Lombardi, who is supporting this thesis with a wonderful mobile observatory, which is right outside the observatory we're in right now. This will be one of the first stations that we'll be using for the Virginian Coordinated Occultation Timing Array. It's a beautiful C11 Celestron 11-inch telescope, and it's already outfitted in an observatory, which we'll be using to observe occultations all night, every night. And it's supporting a team of about 25 students who are itching to have time on telescopes, but just don't have it. So I'd like to thank Leo for the support. And this is an example of the type of shadow that we observe. There's a lot of these every night. So they crisscross Earth in all kinds of different ways, and we observe on a given night about 30 or 40 of these when it's clear. The really exciting science that we do is expeditions. So these kind of occultations that pass over Charlottesville are random asteroids. We usually don't care about the specific asteroid we're observing, but it helps us build an idea of the population of asteroids in the solar system. The really exciting ones are when there's an asteroid which we want to know more about. And in that case, we have to pick from the occultations which are going to happen across the Earth, and you really don't get to pick where those happen. And so you have to bring your telescopes with you and your cameras and your timing equipment wherever the shadow might go. And we have gone quite a few places to do this. So we have been all up and down the eastern coast in our cars, and we've flown out to the western United States. We actually drove to Kansas this summer. That was fun. These are all for what we call the higher priority asteroids. So either spacecraft targets or asteroids which have specific features which are only detectable through occultation science. So rings, small satellites, for example, things which you need an occultation to observe. If you point a Hubble Space Telescope at a very distant asteroid, it's nearly impossible you'd be able to detect that it has moons unless you saw a secondary blip from an occultation. We've also been some other places which are fun, and I'll show you kind of what these are for. So so we have access to a small fleet of telescopes, about 8 of them now, which we can support with occultation timing equipment. These can be driven up and down the east coast of the United States of America, and we can fly a few of them. We've just been supported with a nice grant from the Jefferson Trust to transform some of our telescopes into flight-worthy telescopes, which we can check in as checked baggage on a United Airlines flight and take wherever we want with us. I'm going to kind of go through some exciting ones we've done before. Dwarf planet, not a planet, sorry, rest in peace. Pluto had a very exciting occultation from the Northern Territory of Australia and Indonesia a few years ago. I think this is 2021. Pluto is very exciting because it has a non-negligible atmosphere, which has the capability of refracting light into a. Actually, we'll use the whiteboard for this if you don't mind.
Yeah, sure. Yeah.
So in a standard occultation, you'll have your regular dip for the star brightness, kind of noisy, but it goes up and down like this. This is where the occultation occurred. For an asteroid that has an atmosphere, if you happen to be standing near the center of where the occultation will occur, the air in the middle will actually refract the light into what it's called a central something. And a very, very sharp spike will appear in the data where all of the light is basically focused like a telescope into your telescope by the planet itself. So that was what they were hoping to see. I can't show you the picture of what the light curve looked like really because it's under embargo. But they were able to see something like that, which is really exciting. Yeah. Unfortunately, that's what I said too. Does that make sense? That's kind of it's a.
So we've heard other speakers here talk about that too. They say, hey, I want to show you this, but you can't. What is that? What does it mean? What is the purpose of the embargo?
So the idea is it helps protect the proprietary nature of the findings, and so that you can set. So the people who are leading the study, they've worked very hard to procure these findings, and they've worked very hard and diligently to prepare them formally and make sure that their methodology is sound and they've not made any scientific errors. And it's fair that they have the chance to be the first to present those findings formally. And if it's shared publicly before then, there's a chance that somebody might take a picture of it, share it online, and then they've lost the element, not the element of surprise, but the element, the recognition that they are deserved for their science. And so members of a team who are working as under somebody who's leading a study, for example, someone, I don't know who, I wasn't involved in this campaign, but the person who was leading the campaign to observe Pluto has asked that the people who are assisting with that campaign keep the findings quiet so that they don't spoil the release of the data. Anyways, they were able to. I can share that they were able to see it because that's public, but the specific details of what the plot looks like are under embargo, so I can't share that. This is one of the mission targets of the Lucy spacecraft, Ptolemy, which has become one of the most interesting ones of the sample of 7 asteroids it's visiting. So the first big campaign to observe it was observed from Rockingham, North Carolina, by 2 different teams of UVA observers. This team actually observed a double dip of the asteroid, which is kind of hard to see over here. I'm spoiling the surprise over here. But they saw the light go, they actually saw something like this, which basically means that there's some sort of topography, like a mountain or a canyon that hid the occultation. The canyon revealed the starlight again, and then the canyon went back out behind view, and that there means that there's some sort of a peanut shape up there. What was very interesting from this event is that these 2 stations down here did not see any occultation by the main body of Ptolemy, but they both saw a congruent secondary, much shorter event, much farther away from the main body, which is indicative that there is a very small moon that orbits Ptolemy, which is very exciting for a spacecraft because there's going to be pictures taken of this system in about 3 years.
So the size of these asteroids, how big did you say they are?
This one's a few hundred kilometers, I think. This is a really large one. I think that the moon, which is called Shaun, from Shaun the Sheep. I don't know if you're familiar with the the British studio. I forgot the name of them, but they named it. That's it. Yeah. Yeah, they named it after the sheep.
So a few hundred meters, and how big is it?
200 kilometers, so it's quite large. Yeah. And I think this is a moon of a 5 or 10 kilometer size, so it's relatively large. But it's still small because it's so far away. If you're looking at 5 or 10, remember this is as far away as Jupiter is. Jupiter is enormous, and we can still barely see some detail on what the stripes look like. Imagine going out there with a refractor and seeing the detail you see. That's hundreds of kilometer scale. Actually, no, that's thousands of kilometers. Each of those stripes is thousands, maybe tens of thousands of kilometers large. And you're able to pull out detail, sub-kilometer detail, if you're looking at what's going on up here, which is a testament to the power of these occultations, that you can really see some immensely detailed stuff with these. So they obviously found this moon, and they were like, oh my God, we need to get everything out there. Oh, question. Oh, cool. Great. So they found this moon, and they were like, oh my God, we need to get every gun that we have on the planet pointing at this thing right now. And so the team at the Southwest Research Institute, which is building the spacecraft, or built the spacecraft, decided to put together everything they had. They launched a 100 telescope campaign across the central United States. This is one of the training nights. There's 100 telescopes and 200 observers. It was the largest centrally coordinated occultation campaign in history. That's me and my buddy Robin out in a field in Kansas. And they got the main planet, and I'm very happy to report that one station out of the 100 saw the moon again, and one of the observers on that team was one of our very own UVA observers who just graduated last year. So we're very happy. We pat ourselves on the back for that one. That was pretty exciting. Another one of the survey of asteroids that Lucy is visiting is called Euripides. We drove to New York to look at it. There was a lunar eclipse going on at the same time, which is pretty cool. We were on a riverbank in sub-freezing temperatures for a few hours with a big telescope, and we saw it happen. This is what we saw. Much noisier data than we would have liked, but there's evidence of that little second bump in here, which means that there's some sort of topography on the edge of the asteroid. There's a lobe on the edge almost, which suggests that and I'm really hoping that when the spacecraft gets here, they're like, hey, what do you want to name this thing? Because there's going to be a really good picture of what this thing looks like, and we were the first ones to see it. So I feel like we should have some sort of credit for naming. What's that? Yeah, well, we were thinking Mount Becky Williams because she recruited all of us into the group. But yeah, we have a team of observers traveled to observe another Trojan asteroid, Mathilde, from North Carolina, Wilmington. Beautiful sunset there. That's a terrible car for the Occultation Group because it's we spend about twice as much on gas to get that thing to an occultation than we do anything else. But it's also the turn signals, you have to use your arm to signal where you're going. This is a fun one. The Kuiper Belt object 19521 Chaos is an enormous 500-kilometer wide dwarf planet in the distant outer solar system. It's a really cool name too, Chaos. We have a tradition of listening to music with the asteroid name in it as we're occulting and taking data on it. And there was a lot of really fun ones for this one, heavy metal. The uncertainty on the prediction of where this asteroid would be, they didn't really know where the asteroid was going to occult because it was so far away. And like I mentioned, a lot of these distant asteroids have very poor constraints on their orbit. The uncertainty on where this 500-kilometer wide asteroid would be when it occulted the star was essentially the size of the United States. So there were about 40 telescopes from coast to coast, all set up, hoping to get a glimpse of this thing and potentially catch any moons that it might have as well. We, the UVA team, it was the biggest deployment we had ever done at the time, deployed 5 telescopes across the Virginia, West Virginia, and Tennessee. There's a line you can kind of draw from between them to try to catch it in the event that we did. We all successfully got data, except for one, which in Virginia Beach, which had clouds over their field of view at the time. Of the 40-ish stations which observed this event, 8 of them saw what happened, which was really exciting. And of those 8, we were 4. So we were very proud of ourselves after this one. We did a bit of a back of the napkin drawing of what the asteroid looks like as soon as we got back. There was already some suspicion that this asteroid was what we call a contact binary, which means that 2 planetesimals smashed together a long time ago and inelastically stuck together. And from what we observed here, you can actually see how that morphology makes sense. There's one planetesimal here and one planetesimal here that have clearly stuck together. You don't form something like this naturally. You don't see a shape like that arise naturally. You see a lot of spheroids arise naturally, and this looks a hell of a lot like 2 spheroids which have collided with the force of a falling moon. And that was very exciting. These back of the napkin ones are really fun to put together. I think some of you guys saw this one too. This is a pretty popular occultation. This was the moon occulting the sun. We traveled to Zanesfield, Ohio to observe it from a summer camp. We also observed another occultation that night just because we were there and we wanted to put a pin on the map. So we brought our telescope along with us. We observed it. It was really faint, a really faint star. And so the data was pretty terrible. So we didn't store the data. I don't know what the asteroid was called, but it was called something. And we observed it from there. But the main event was the moon. That was really cool. Another Lucy target asteroid was this binary called Patroclus and Menoetius. These 2 enormous 100-kilometer scale asteroids which are spinning around each other out in the orbit of Jupiter. They have basically the shadows cross the Earth in tandem. There's basically from Canada down to the southwest. We observed there were 30 telescopes for this one. There were 15 training on each. I should say that all of these Lucy target ones are supported by SWIRI. These are not our own telescopes. And so SWRI, the Southwest Research Institute, provided 15 telescopes for Patroclus and 15 telescopes for Menoetius. And results are under embargo, so I can't show you them, but it's a very, very nice picture. But this is cool, I think. This is a really pretty sunrise. The events are oftentimes at very inopportune times of night, which I'm sure you are all familiar with. Your spouses and or family must, don't always appreciate what time of the night you have to be awake. One of our members' mothers calls us the crazies because we were up at, this particular event was at 4:40 a.m., I believe. So really early in the morning. This is a fun one. This is a binary asteroid, Arecibo. This was the first asteroid to be discovered to be binary through occultation. So they observed an occultation by it and basically saw two very distinct dips from multiple telescopes, which indicates that there's two asteroids there, not just one. We journeyed all the way from Virginia up to the northern upper lower peninsula, Michigan, to observe this one. This is one of our telescopes. We brought 3 telescopes with us. These are our own telescopes. These are the light curves we saw of the 3 events. These are the 2 successful stations that observed data. You might ask what happened to the 3rd telescope that drove all the way to Michigan. Does anyone know how long that drive is? 14 hours, exactly. Yeah, about 14 hours to get there. All 3 of our teams, we had about 10 observers travel with us. These 2 stations obviously got good data. The 3rd one, the laptop died about 45 seconds before the event happened. So that was a real kick in the pants. Nothing else to do but to pack up and head home after that. So this is we have a saying that we've learned about 1,001 ways not to observe an occultation. They're very intense things. You have to they happen at a very specific time of night, and they only happen for about a second usually. And so if you're not looking at the star you need to be looking at for the second you need to be looking at it, and your timing is not perfect and all of your configurations not correct, you've missed it, and then it's a shameful feeling.
So that brings up an interesting point in conjunction with what you said earlier about at any given point you see lots of stuff. So when you go and you spend all this effort to go to a faraway place to see one thing, do you at least camp out and get others?
No.
Or is it just that?
So yeah, there's actually we've often thought about doing that, and I'll get to something. We did something like that similarly on a recent trip that we just went on. But on the night of the event, for one of these, it is very distracting. Usually when we're at home and we're observing a lot of events, we have 1 telescope and lots of observers. For these events, we have a lot of telescopes and many fewer observers per telescope. And it is almost every time we have attempted to try to do something where we do more than 1 event than the main event that we're here to observe, we find that they are distracting. And they tend to result in failure when you are focusing on too many things, a lot of things. These ones, for example, your laptop tends to die if you're out there for more than a few hours. And so you want to get set up about an hour beforehand, start setting up everything, especially when it's cold outside like this was in Michigan. We're not going there to see random occultations because the random occultations will happen from Charlottesville, and we're happy to get those here. We're not really interested in drawing what's our important attention away from what we're there to see other things which we can see from Charlottesville. If that makes sense.
It was whether or not you're certain you're out there anyway, and you
right. Right. Yeah. You want to keep your attention focused on why you're there, because we found in the past that if you're focusing on doing too much at a time, you end up losing focus, losing track of what's really important and why you've made it all the way there. And
Is that Dave Dunham you got there?
It is David Dunham. Yeah. Do you know him? Yeah, he's a great guy. We have a few telescopes from him and a lot of great stuff.
I have a question. How are you coordinating the accuracy of the time?
Oh, that's fun. We have a few different methods. There are some cameras we have which have built-in GPS compatibility, which will embed the GPS time from a module you attach to the camera. There's an antenna you can screw onto the camera, and it will literally feed that time into your FITS file, the image you're generating for each frame of the video. We have found a much better camera, which doesn't do that, unfortunately. And so we've had to get kind of creative. Our faculty advisors have devised a homemade module on a serial board with a GPS antenna on its own. What we found is that we can actually, using a program on our laptops, synchronize the time on the laptop to that GPS time from the antenna to guarantee that we're within a millisecond of what we think we are.
So all of the testing sites that you might have are all synchronized within millisecond?
You know, I should clarify, the GPS we're actually using is not for your space on Earth. It's actually for your timing accuracy. I should have mentioned that earlier, sorry. So you're having a very, very precise connection to a GPS is extraordinarily important for all of the things we do, but it's not because of where you are on Earth. You can find that on Google Maps and look at, I was within a foot of this, and that's fine. You get your plenty fine there. But it's actually the timing. Every GPS satellite on the planet, if there was a GPS talk a few months ago, they all have atomic clocks on them. And so you can use that if you can communicate with the satellite, you can actually extract that time and use it for your measurements here. And we calibrate all of our GPS on our laptops to accept that time as true time. And then the system time is embedded into the FITS file, which is accurate to the sub-millisecond at that point. And that's really important. The timing is actually surprisingly pretty much the most important part besides looking at the star. If you have bad timing, you've screwed up generations of observations to come because, and this has happened to us before, they take these observations as fact that you have good timing. And so when you report this to JPL, which is where we send all of our data to NASA through JPL, they update their Horizons database for all of the asteroids in the solar system. If we were off by a few seconds on where our timing was, or even several milliseconds, every future occultation prediction is off, and people that think they're certain to see one happen will not see it happen. So it's very important that we have good timing on our observations.
You send your data to JPL then forwards it to the MPC.
Well, I think it's within JPL. So we actually package it to the International Occultation Timing Association, who then passes it on to JPL. But with hey Siri.
Questions over here.
Yeah, sorry, we have Siri going on my phone right there. What's up, Momo?
Yeah, how far in advance do you get do you know when or not?
Oh, we predict our own. So you can predict these 100 years in the future based on the orbits you have now. The orbits kind of degenerate after time, so you're really only hoping to do these for a few years in advance. But we make all of our own predictions. We have a program that we use that someone's written, which is really nice, which we use to figure out when these are going to happen. Anyways, this is what the oh, Ken had a question back there. You can. They have built-in programs for it there. Actually, they're limiting. I think it's an SCMOS in the. That's the chip is a CMOS, right? Yeah. Right. The biggest issue with an EV scope is that you're limited in magnitude to pretty much, I think, below 10th magnitude, and the occultations which occur below 10th magnitude are pretty rare. Right, but these events are very short, and so you can get 17th magnitude if you're integrating for a few minutes long, but the occultations are only a few seconds, and you have to capture frames we like to look for about 4 frames of blink out, which means that if it's a second long, each of your frames needs to be about 1/4 of a second. And at 1/4 of a second, an EV scope can only look down to about, I think, I would guess 7th or 8th mag. That's still really great if you have a bright star. There's a lot of science that is being done with EV scopes. I'm not sure how the timing is constrained on them, but if you guys have EV scopes and you want to talk about doing occultation science, let me know. I'd be happy to kind of talk to you about how you can do them. This is the plot we made from our Arecibo, the binary asteroid expedition. This is one of our positive UVA chord. This is our negative UVA chord. There's one really sad one in between, which had a laptop die on it. Those are where we saw those happen. This is what the profile looks like. Just by chance, we almost missed this one. There happened to be another occultation by a very faint star by Arecibo about 2 weeks after this, or 3 weeks after this one, just across Virginia. And so we were able to get 5 telescopes across the distribution of this asteroid. 1, 2, 3, 4, 5. That one was a negative from Charlottesville. That one right there was a mobile team in between Fan Mountain and Charlottesville. This one right here is Fan Mountain. This team is exciting. Two of our observers saw the main asteroid and then saw the binary companion, which is really cool. I'm really sad they didn't see it on their screen at the time because they were apparently dancing around the telescope listening to music for the asteroid and didn't see it happen in front of them. And I kick myself every day for not being on that chord because that would have been really cool. And that was my team with just the moon. It looks like very cool. Oh, this is a fun one. We do a lot of studying of near-Earth asteroids because they have a particularly pertinent value to people living on Earth, whether you're an astronomer or not. Many of these near-Earth asteroids, near-Earth asteroids are asteroids that are within a certain radius of Earth's orbit or happen to intersect Earth's orbit at a certain point. And many of them are labeled as potentially hazardous asteroids, including this one called 3122 Florence. Florence recently flew by the Earth, and the Earth-Moon system perturbed its orbit in an uncharacterized way. And there's set to be another Earth pass by in some number of years. I can't remember if it's 10 years or 100 years, but it's coming back at some point. And we wanted to see how much this previous flyby has influenced the coming flyby. They didn't think it was going to crash into Earth, but maybe after it's passed by Earth once, there's a chance of impact. And this is our distribution. We sent 3 telescopes out. We were joined by 2 more observers. And we were hoping to see this blue area is the width of the asteroid. The red bars are the uncertainty. And if the prediction, which is the prediction that says that we're safe and we're not going to be hit by this asteroid, is correct, the asteroid will be perfectly centered on this green line. So that basically all 5 of these will see the asteroid, or maybe this one won't, but it'll be close. And you'll see these 3 in the middle will certainly see something. And that means that we're in the clear and that we don't need to worry about this asteroid in the future. This is what we saw. So there's several, I think tens of kilometers of offset in where it was and where they thought it was and where it is now. So these 2 teams over here saw it. These 3 did not. And almost poetically, while we were out in the field, what sounded like an air raid siren went off in the region right next to where we were at about 10:30 p.m. at night in rural Pennsylvania. We think in the end it was a power plant, but we sure as hell didn't know that then. And it speaks to the self-preservation of scientists, how much they value it, that happened right before our event, and not a single one of our teams thought we need to get out of here. And every single one of them stayed on their telescope and took the data and then packed up leisurely and left. And only after did we realize we could have been in danger and maybe should have left. But it's okay. I don't know how many of you guys have watched a lot of film, but there's a pretty good movie about what happens when you try to look at asteroids and comets which have uncharacterized trajectories. And so we're hoping this doesn't happen in our study of Florence. Given that JPL hasn't sent out a notice about this asteroid, we think that they have updated the orbit and we're still A-okay on the trajectory. But I certainly don't want to be Leo DiCaprio in this movie. So if anyone asks, I wasn't involved in this observation. All right, now this next set of campaigns are the ones that I'm really excited to share with you guys because they're very recent. And we have results which we can actually share with you because we've led the team, the expeditions, and they're very exciting. So the MBR Explorer spacecraft team, which the Emirates is launching to these asteroids in 2028. Like I mentioned earlier, there are these 3 really uncharacterized asteroids, and the UVA team has just concluded a series of 3 expeditions to observe a single one of these asteroids, 599801999 SG6. The first of them passed over South Africa. It passed over the largest telescope complex on the continent, which includes a 10-meter, the 10-meter SALT telescope. This is what the SALT telescope looks like in real life. It's a really fascinating telescope. I can talk all about it at a different time. We traveled out there. If you can't tell from this picture, weather was a pretty horrible issue. And on the night of the event, after we had traveled 8,000 miles and spent about $10,000 of grant money to get there, we were looking at snowy skies. And I was sitting in my car, which was a real shame, but pretty nice vacation. So you can't complain too much. And you pick up your you pick yourself up and you get on to the next one. The next one happens to pass over a little bit closer, Georgia and South Carolina. This is the path of the asteroid. This is a cloud cover prediction. We were also affected by weather, but we had a team of about 11 UVA students. We dropped 6 telescopes across the shadow path. This is our hotel room, very saturated Family Guy. And we were joined by a few other observers who were unfortunately not able to take data when we wanted to. So we had these big gaps in our coverage, which is unfortunate. But we were able to produce these maps. We have one chord here, which we're a little bit dubious on if the detection is actually real, but we trust all of the detections here as factual. And so this is the first result for what the shape of this thing is. Very strange flat edge here. The ellipse is a very poor fit to this thing. We just include it for characterization purposes. But there's certainly an edge which seems to be more rounded or pointy, and one that is more flat. And so for the third campaign and final campaign, we drove about 22 hours one way to Wichita. We were joined by the same team which does the Lucy expeditions, SWERI. They provided 13 of their own telescopes, and we were joined by 5 others across the central United States. This is a great little picture of all of the telescopes we were working with all at once, all training. Weather was also horrible for this one, so our signal was difficult to extract, but, oh no, where's the picture? Oh, this is here we are, okay, that's weird. This is a fun little time lapse of assembling them if I want to continue this. Oh, well, that's annoying. This is a fun little time lapse of us assembling our telescopes. Yeah. And there's a really cool, you'll see the moon rise in a minute right through here. This is over the course of about 4 hours in a night. There's the moon, look at that.
You should contact us here at CAS next time you have a big
Deployment.
Deployment, and we might
Oh yeah, we'd
wrestle up some extra cars to haul your people.
Oh, we'd love that. So we had 4 observers for that particular mission, and each of those 4 observers actually deployed 2 telescopes. And we observed 4 of them remotely with a pre-generated script, which was the most intense experience ever. You had basically an hour and 15 minutes to configure 2 entire systems, which are separated by 3 miles. You had to drive between one of them and the other one. It had just rained, so all these dirt roads in Kansas were muddy. And we had to get a U-Haul van, and it got stuck in the mud, and it was just but all things considered, if I can please operate this again. No tornadoes, and we got a wonderful data set on what this thing actually looks like. It's what we think of it as a lily pad. So this is the flat edge we think we saw earlier, and this is a pointy edge. Just thrilled about that. Really wonderful results. We're compiling, or I am compiling these findings into a publication, the results from this campaign and the Georgia campaign. And we are very excited to share those. But no pictures of this, or maybe you can. I don't care. It's going on the internet anyways. So hopefully nobody minds too much. I'm allowed to do it because it's my data, so I don't know. There is, I really wish I'd included some pictures from a recent event, and I'll talk about it more. It's okay. It's not a big deal. The last one I want to share with you guys is one which occurred what's the date today? The 1st. It actually occurred yesterday in Universal Coordinated Time. Yeah, no, of course.
Specific journal to which you publish these sorts of things, your journal of observation?
The Astronomical Journal, the AAS, the American Astronomical Society, is likely where we'll share this, or it might do something smaller. I'm not sure. There's not one. We have discovered a star with occultations before. We published a paper on that in the Washington Double Star Journal, or I think that's what it's called. So there's other science you can do with occultations, but for the sake of time, which we're running a little bit low on, I'm not going to get into that side of the things, but if you're interested, I can talk to you about it. But yeah, we'll probably one of the American Astronomical Society's journals. So yesterday in Universal Coordinated Time at about 6 a.m., which is about 2 a.m. local time here, but where we were, it was minus 10 hours. Does anyone know what where minus 10 hours from UTC falls along the Earth? We were in about 24 hours ago. I was on an island in the Pacific observing the dwarf planet 50,000 Quaoar, which I was telling you about before. You guys have dragged me away from a wonderful beach in the central Pacific Ocean. We were camping in this canyon here, and this is a view I got on my DLSR from our mount. Now I'm here talking to you guys about what I was doing there. I'm joking, of course. I'm happy. We were coming back anyways. We were observing an occultation by this dwarf planet Quaoar I was telling you about earlier. This is the one that at the very beginning of the slideshow had these really interesting. I didn't tell you about them then. It has this really interesting set of rings around it in the outer solar system, and there are these minor, not full dips in brightness before and after the occultation, if you happen to intercept the right part of the ring. And so our interest in this event in Hawaii was to characterize these. Oh no, I've lost the presentation. This doesn't want me to share it.
Don't take a picture of this. This is that's the word you use.
Proprietary, yeah. Oh, dude, come on, man. Our plan was to see if we can detect these rings. There's only one part of the ring. These rings are very amorphous, so they have. There's only one part of one of the rings in which the brightness of the star will drop completely to zero, like the main body, which we saw here. This is about a 3 or a minute and a half long occultation, very long event. And the other rings are only detectable through their diffraction effects on the light from the star. So they're very loose collections of rock and dust, and as they pass in front of the star, they basically ripple the light that passes through it. So we essentially, this is one telescope's data. We shipped our 24-inch telescope all the way out to Kauai, to the Pacific Missile Range Facility on Kauai, and combined it with the apertures of telescopes from a 17-inch telescope, a 10-inch telescope, a 14-inch telescope, an 11-inch telescope, and a 10-inch telescope. And the idea is by combining the light from all of these telescopes, we're essentially simulating a telescope with a mirror of about 38 inches in diameter, which we think is large enough. The noise actually, this is very noisy right now, but as you combine the data, the noise decreases with relation to how many telescopes you're stacking up. The idea is by then we can hopefully see a diffraction effect of one of these rings and characterize. There's actually 2, potentially 3 rings around this planet. It's enormous, 1,000 kilometers wide, and the rings are way out past where they're supposed to be. It's a very funky object. We think a moon collided with something else and exploded, casting a ring around the planet. Anyways, very odd things, and that's where I was about a day ago. The last thing I'd like to kind of share, if people are interested in watching it, this is kind of what an expedition looks like, including what an occultation looks like. Now it's going to hate me pulling this video up, but that's okay. So we make these little these are for our grant, our donors, basically. We make these, is there gonna be sound on this? Is there a way to get sound on this at all? You know, is there,
Yeah, through the projector.
that's perfect. If we can get the projector speakers, that'd be great.
I assume that they're already max. Yeah, so it's already at max volume.
All right. Well, there should be some sound coming out of here. Let's see. Is it set up through here properly?
I think it may be tricky to do on time available.
Of course, yeah. Well, what I'll do in that case then is I'll skip to the part where the occultation actually happens. And so I'm going to, this is the star that we're studying here. Helpful little ring. This is for SG6, the spacecraft asteroid that we're studying from Georgia. So if you keep your eye on this star, it'll zoom in slowly over time. Our editor did a good job with that. We'll see this particular event was predicted to occur for about 0.6 seconds in duration. So keep your eye focused on it.
Don't blink.
Yeah, don't blink. That's the number one thing. You miss it. It's a bug on our screen in the field. It was very humid. What, about 10 seconds? Yeah. Oh, 5, 4. Look at that. So that was pretty, that's how it is. A little grainy on the big screen, but that's okay. And that's kind of what an occultation looks like. They're really cool to watch in the field. And that concludes my talk. I went a little bit over time, I think. I hope you don't mind. Questions?
Let me get the mic back to that. Hold it. Gotta get past the mic back.
Does either JPL or the association you mentioned, intermediary, have standards in terms of like the software you use, the methodology?
Right.
So that all, and builds an aggregate database so that all of the different groups.
Right. Yes. Yes, they do. There's a lot of different ways you can observe these. It used to be back in the 60s and 70s. You would be looking through your telescope with a clicker, and you would, you would have a radio next to you that would record. That would be kind of intermittently like playing the time, because you can actually get pretty precise time from radio, and you would click your buzzer when you saw the disappearance of the star, and then you click it again when you saw the star come back, and then you'd have to time your reaction time to kind of find a median reaction time to. Since then, they've developed analog cameras you can use for this with timers, and there's a million ways you can do it. They have made sure that there are specific ways which are verified to have accurate timing, and we work with them obviously to make sure that we're accurate. Yeah.
And the only other question, was that just normal noise, like, you know, atmospheric fluctuations and so forth, the data points,
yeah,
you know, going up and down on it?
This one is actually, this one's noisy because it was we analyzed it in the field. If we'd sit down with this and actually do a more rigorous analysis, and the noise I think would actually diminish pretty significantly. This is just rough to see if we'd see the actual thing happen. So it's, yes, it's the noise for most of these is atmospheric, and but you're right though, it is atmospheric. It's the fainter the star, the more noisy your data is. This was a relatively faint star. It's about 14th mag. It's not 10th mag. So, but this is on a 24-inch telescope, so it should be much cleaner than this, and it will be once we look at it again. This is just very rough analysis.
Questions? Another question? One more question?
Any more?
Anybody online?
Nothing online.
Well, I'll share one last thing before I let you guys have the rest of your evening. Is that I gave a talk about 2 years ago on star formation in a project I was working on with Sophia. I've just last week, about actually exactly a week ago, submitted the first paper we've written on the subject to the APJ to basically on a really interesting massive protostar. And so if you're interested in that, you can talk to me, and I'm happy to share all kinds of fun details about this.
I did read it. I think I got to about here, and my wife said my heart stopped. But no, it's good stuff. It's obviously interesting, but it's going to take me 3 reads to figure out what the hell it's saying.
Well, yeah, there's a jargon which makes me gatekeep the really fun information in here, but I'm happy to talk about this if you guys are interested in star formation and massive protostars.
So you said in your resume, it says that you are all about star formations. That's what you're studying?
Kind of. I mean, I feel like mostly at this point, my main gig is occultations.
Oh, it is?
Kind
Okay.
of, but neither of those are what I'm studying formally. These are my research teams that I'm on as a side.
Gotcha.
And so I'm a student in this one, and I lead the occultation group at UVA. We decide what we do. We're entirely student-led. We have a team, a management team, which decides which occultations we're going to observe and where we're traveling and how we get money. And we're entirely student operated. Georgia knows that. We're all of our observers are students. So that's really fun to do. This is maybe a little bit more technically challenging, but it's also rewarding in its own way. They're very different.
Yeah.
You're in the field actually for occultations, and you're using telescope data that somebody else has taken for you with this,
Gotcha.
which is less exciting, but also still pretty fun.
Well, Teddy, that was fantastic. Appreciate it again.
I don't think it was recording.
What?
I don't think it was recording.
Get out of here. Not my fault this time.
Joking.
So I don't know if we gave you one last time, but if you don't have one, so this is our CAS Astronomical
Oh, thank
Society coffee cup for your caliente cafe.
Thank you so much.
Thank you. Thanks for
Appreciate
coming
it.
and
Of
doing this
course. Yeah,
again.
of course.
Appreciate it.
All right.